My name is Andrew Millward, and I'm going to briefly demonstrate the Arduino to Arduino communication that we've developed. As you can see, connection is established between the two devices, the master and slave. We can send commands through. It can interpret the commands, send a response back, in this case 28 random bytes, decide to set the pin for the device, receive a response back, and drop connection. In addition to those aforementioned points, we can also modify it to connect to the LR100 device, send a similar command, but this time using a checksum to allow the LR100 to respond, and then drop connection.
So the way that the code works is that on the left side we have the master, and on the right side we have two different slave Arduinos. So the way that it works is that it will connect to one of them and begin querying based on what we have inputted. So we see that we connected to one of them, this Arduino, and then we're querying item 1. So we were able to get data back from one Arduino back to the master, and same with the other Arduinos.
So encryption was not required for all the packets which were transferred between the sensor and the host. It was mainly required for the authentication purposes. So first we used a basic encryption method where this is the message sent from the sensor and this is how the host received it. Then we upgraded our encryption to use the one modernly used by most companies, the SHH-256, which is a hash function built by the NSA. We also incorporated a CRC, which was used to make sure there was no accidental damage to raw data.
Vbo3 commands can be sent to the LR100 in order to pull data from the sensor. By looking at figure 1, we see that each command begins with a serial number, followed by the order number. Next, we indicate whether this is a read or write command with either 4A for a write and 4B for a read. 09 is then used to indicate the length of the following bytes. 00 represents the number of device addresses. And next, we construct the data of the command, and this structure can be seen in figure 2. The data portion of the command will always begin with 01, 05, 03, FC, and then be followed by the address of the parameter that we are working with. We finally end the request by appending the CRC value to the end. By following this structure, we were able to construct the Vbo3 command seen in this table.
For the Arduino subsystem storage, we use the extended database library to enable the EEPROM memory of the Arduino, where we use the simple reader and writer wrapper functions of the EEPROM, where we can essentially store 1 kilobyte worth of data for every transmission of message, and we can allow for multiple LR100 sensors as well. To create this database structure, we just use the simple sensor ID as well as the sensor data to be passed through, and once the data is decrypted, we can just create a database table and pass it on to storage for IoT2040. Here is a successful read and display of the serial monitor.
Since the IoT2040 runs on Linux, we decided to write a script that will both connect and log incoming data. The first, by putting the port that the Arduino is currently connected to on my computer, I will connect to it. You now see we're connected. Next, I will log data by sending some data to the Arduino over Bluetooth. Since we're done logging data, we'll quit out of this and take a look at what's on the Arduino. We see a new data underscore test text file, and if we see the output of that, we see that the IoT has the ability to read incoming data over the serial port.